feel like most everybody's here, so we'll go ahead and get started. Okay, so we ended class talking about this idea of like dissolves like. So things that have similar polarity, either both being polar or both being nonpolar, are likely to be soluble in each other. So that's going to most of the time be the place we start to decide if something is soluble. If you're given more specific data, like, where is it? This one, where we're actually given energy associated with the delta H of the solute, the delta H of the solvent, the delta H of the mixing, then what you're looking for is it exothermic or maybe just slightly endothermic? And then we would consider it soluble, okay? So if you don't have that specific of information, then you're just relying on this idea of like dissolves like. And some of that is going to be maybe not quite as clear cut. So like in this example, it's very obvious. These three things are polar, okay? When we're looking at a lot of these examples, we're using things that are either have oxygen or nitrogen groups in them, and that's what creates the polarity. So we're kind of going more away from simple molecules that we would draw Lewis structures of and more towards carbon-based molecules. That shouldn't necessarily be more difficult because in a lot of these carbon-based molecules, they behave really typically. So like, remember we said that things in the carbon group tend to have 4 bonds. Nitrogen tends to have 3 with that lone pair. Oxygen tends to have the 2 lone pairs and the 2 bonds. And simply because those all follow the tetrahedral electron geometry, and then the lone pairs offset that geometry. If you've got a nitrogen or oxygen in the molecule, you can almost guarantee that it's polar. So when you're looking at a lot of these, you're really just looking for, is it just straight carbons and hydrogens, or does it have some oxygens mixed in there or some nitrogens mixed in there? That's going to be a lot of the molecules. There may be a couple that are a little bit more complicated, but a lot of the times that's going to be it. And then also remember that ions are like an extreme version of something being polar, because when we say it's polar, we're saying there's a partial positive and a partial negative side of the molecule, or points on the molecule. Whereas if we're talking about ions, now it's just a full positive and a full negative, okay? So when we look at ions, typically we think of them as polar, with the caveat that if it's a salt, like an ionic compound, we have to check the solubility rules if we're talking about, is that soluble in water? So energy, that allows us to be very specific. If we don't know anything about the energy, we need to consider like dissolves like, and if it's an ionic compound, we need to consider the solubility rules, okay? The other thing that kind of comes into play here is, what about if we have portions of a molecule that seem to be nonpolar and then portions that aren't? Like, how do we decide in that case? So like I said, these ones are really clear, polar, 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 nonpolar. So it's very clear what our answer is there. But these ones over here start to get into this gray area. And maybe before I get to that, like fats are a very common example of this. So I'm not counting here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I was trying to do like 20. So 12, 13, 14, 15, 16, 17, 18, 19, 20-ish. Okay. So remember when we draw molecules like these little zigzaggy lines, what we need is there's a carbon at each one of these bends, and then it has however many hydrogens to need 4 bonds. So like the one on the end here would be a C with 3 H's, just like we have it written there. But then a carbon here that's bonded to 2 other things would have 2 hydrogens, because then it has a total of 4. So that's like this CH2, that CH2. It's just when we get to really long molecules, we don't really want to write out CH3, CH2 that many times, so we'll often draw them. So this is roughly a basic fat, like, oil, like olive oil, or the fat in butter, or stearic acid, I think is that one. When you get to the end of this molecule, though, you end up with a double bonded oxygen and an OH group. These are called carboxylic acids. If you take organic chemistry a lot, like the first 2 months is going to be all the different names of stuff like this. So you don't have to know them now, but I'm just kind of introducing you to the idea, okay? So you have this very polar portion of the molecule. The OH group, behaves a lot like any other alcohol group. That carbon double bonded to an oxygen is going to have polarity associated with it because you've got that difference in electronegativity and the lone pairs on the oxygen. But you also have this really big portion of the molecule that's just carbons and hydrogens. So if I bring another nonpolar molecule near this, it actually has the ability to be attracted to, or if we're talking about forming a solution, to dissolve into this portion of the molecule. Whereas we might actually be able to bring something polar over to this portion of the molecule and have it attracted to that. The classic example of this is soaps. So the way they make soaps is they take a fat and they put a base in there in order to pull that hydrogen off. And then what's left behind is just a negative charge, an electron, okay? So that actually makes that end even more polar because, again, now it's not just a partial charge, it's a full negative charge. So when you have this, you now have a very polar end and a very non-polar end. And like, let's say you're washing the dishes and you have some oily residue on a pan or something. You put a soap in there, that oil gets attracted to this part of the molecule. The water gets attracted to this part of the molecule, and then you wash it all down the drain. So the water goes down the drain, but it also takes that end of the molecule with the oils attracted to it and leaves, okay? A lot of you guys are biology students, so like the lipid bilayer, isn't that what it's called? Anybody? I think so. Yeah. So like that's where the two ends of a fat will stick together and form kind of that water-soluble barrier on a cell, and then it has the polar ends that are soluble in the water. Okay, so lots of different examples why that's important. Okay, so what we're really saying is that there could be portions of a molecule that could be soluble in one thing and portions that could be soluble in something else. So in this example, which of the following will be most soluble in water? It doesn't just say which will be soluble, which will be most soluble, and then which is most likely to be soluble in toluene. So remember, toluene was our non-polar thing that we talked about in the previous question. So I'm going to keep with our highlighting pink polar, the yellow's non-polar, okay? So looking at those molecules, whichever has the least non-polar characteristics, that's going to be most likely soluble in water. So the non-polar portion is that carbon-hydrogen groups. So this guy has the least carbon-hydrogen group, and then that OH group that we know is soluble in water. So this one's probably the most not probably, it is the most likely to be soluble in water because its polar portion is going to have more influence because there's less of that non-polar portion. The more carbons and hydrogens you get, the more likely it's going to be able to be dissolved into something non-polar. Okay, so for the toluene one, this longest chain here, where there's lots of carbons and hydrogens, that's where you're going to have more of it dissolving in a non-polar solvent. So it's like basically which part is more dominant. So when we look at a fat, not a soap specifically, put that hydrogen back on there. When we look at a fat, it kind of makes sense now, you know, like an oil. So we would never think of oil as being soluble in water, even though it has this portion on the end that is polar, because that non-polar component is just so dominant. So it's not always super clear cut, but the question's going to have to ask it in a way like this one where it says which one's most soluble or most likely to be soluble in whatever. So some of it's going to be guessing, but the question will be worded so that, you know, you can guess it. But a lot of these you would just have to do an experiment to tell whether it's soluble in a non-polar one or a polar one. Mm-hmm.
He said the bottom example was soap and oil.
Yeah,
Water.
so when it has the hydrogen on it, that would be like any kind of generic fat, like biological fat. Now, I use the term oil. When I say oil in this context, I'm talking about a fat. When I say oil, when we're talking about just carbons and hydrogens, that's oil, like oil from the ground. So those are two different things, because oil from the ground is just carbons and hydrogens. There's no oxygens in there. Once you get into a biological system, that's when you get the oxygens in there. Okay, so next application of this, I want you guys to take a look at these 4 vitamins and take a guess. It is just a guess at this point, but take a guess whether each of these will be soluble in water, so something polar, or fat soluble, something mostly non-polar. So to help you along in this, if you're stuck at all, I'm just going to highlight the portions of each molecule that would exhibit some polarity. Okay, so knowing that, just take another minute or so. You're guessing whether soluble in fat or water. Okay, so these are guesses, but looking at vitamin C, there's lots of things on that molecule that exhibit polarity. And the other thing that I'm noticing is that they're all very like spread out in the molecule. So it's not like there's a particular side. Like if you look at vitamin K, it's got two areas, you know, when an oxygen's bonded to a carbon, that's a lot less polar than if you also have that oxygen bonded to a hydrogen. Because we know that when we're talking about intermolecular forces, that OH bond creates a significant partial negative on the oxygen, much more so than just a carbon bonded to an oxygen, okay? So those do have some polarity, not nearly as much as the OH, but also, do you see how on vitamin K, they're kind of isolated on one side of the molecule, or I guess two sides, not all areas? Whereas in vitamin C, it's all really spread out, okay? So my guess is vitamin C, not just my guess, I know. Vitamin C is water soluble. And when it comes to vitamins, this is like the stuff you can't really have too much of it. Like, you'll just pee out anything extra. So, like, my mom was really into, like, vitamins when I was a kid. So when we had, like, a cold, she'd make us, like, take, like, a chewable, like, 100 milligrams or something, which is, like, more than, like, your needed daily amount of vitamin C. But she'd make us take one of those, like, every couple hours. Totally overkill. But it's not going to hurt you because you're just going to pee out any extra. Vitamin K, that one, like, I actually had to look it up in my last class because I thought I knew what it was, but when I saw those two carbon-oxygen bonds, I was like, am I sure? I'm not totally sure. So it's okay. There's going to be some that are question marks, and you wouldn't necessarily know for sure. In a question like this, if you were asked on the homework or on a test, like I said, the wording would be important. It might say which of these are most likely to be soluble in water, okay? So I'm going to say vitamin K is possibly soluble in water, but not most likely. Vitamin C looks very likely. All those OH groups all spread out over the molecule. Vitamin B, B5, also looks like that. Lots of polar groups, very well spread out over the molecule. Vitamin K, I'm not quite sure. If you look it up or if you know this, vitamin K is fat soluble. So that basically confirms that, yeah, those two groups are not really enough to push it over the edge. Okay? Vitamin B, though, is water soluble. And vitamin A, if any of these are fat soluble, it's going to be vitamin A, because it has this huge portion of the molecule. It actually looks a lot like a fat, just with a ring on the end instead of a straight chain. And it's just got that one OH group on the end. Okay, so I'm going to assume this one is fat soluble, which it is. So these are the ones that you can have like toxicity if you have too much vitamin A, either taken as like a supplement or this doesn't generally happen with people eating it unless you eat like liver. That's how you can have toxic levels of vitamin A, but it's because it's stored in your fat. So you won't actually get rid of it if you have too much of it. Okay, good? Any questions on that? All right, so the next stuff we're going to talk about is if we say something is soluble, that doesn't actually mean like it's just going to infinitely dissolve a ton of the stuff. And you guys have like practical experience with this. If you have a cup of coffee or tea or something, you can put like a spoonful of sugar in it and it'll dissolve just fine. But if you're making like lemonade or Kool-Aid or something like that, which has a ton more sugar, and you try to dissolve, a cup or two of sugar in a gallon of water, it's probably going to be pretty difficult to dissolve that much sugar. And if you keep adding it, there's going to hit a point where it won't dissolve anymore. Okay? So when you've put some in, and it's able to dissolve into the liquid, we would say that that's unsaturated. Like you're still putting, a cup of tea with a spoonful of sugar. That's going to be unsaturated. Saturated would be where you've dissolved everything it can possibly hold. And if you put one more teaspoon in, it's not going to dissolve. The only way you can really know if something is saturated is if it has solid at the bottom. So you can never quite be sure unless you've put in enough that all of it's dissolved and there's leftover. And if there is leftover, you know that it's saturated. If it's, you mix it up, you shake it up, whatever, no more dissolves, there's a little bit of solid left at the bottom, then you know the solution is saturated. It's got as much as it possibly can hold. And then there's this other component, which involves changes in temperature. So with solids, this is different for gases, but with solids, as you increase the temperature, you're able to dissolve more. So we have this chart on the next 2 slides down, which is for some ionic compounds, and it's showing us how the solubility, or how much you can dissolve with changes in temperature. So, down here, like room temperature, 20 degrees, with these salts, you can have a certain amount. As you increase the temperature, most of them, the only one that doesn't is this lithium sulfate. I have no idea why that is, but whatever. Most of them increase the ability to dissolve more. Like you can dissolve more solid the higher the temperature is. Again, it's easier to dissolve sugar in hot tea than it is in cold water. Okay, so how does that relate to this supersaturated thing? So supersaturated is when you heat something up and you dissolve, let's say sugar, into it, and you dissolve more than would normally be able to dissolve at a lower temperature. So you get it almost a saturated solution, or maybe it is saturated, okay? You dissolve lots and lots of this sugar into, we'll say, hot water. Then you cool the water down. So let's pretend at cool water you can hold 100 grams of sugar. And the hot water you can hold 120, okay? As you cool down that hot water that has 120 grams of sugar, you cool it down. If you do it really carefully, you can keep all 120 grams of sugar in the water. So that would be considered a supersaturated solution, like it has more than it's really supposed to at that particular temperature. So, was that a question?
I was just going to say, I looked up lithium sulfate.
Oh, did you? What does it say?
Well, because when it dissolves, that is an exothermic reaction. So as the temperature rises,
That's awesome. Thank you. That's so cool. I wouldn't have thought that, but you're right. I knew that lithium sulfate was exothermic, but that didn't cross my mind that was related. Fascinating. Okay, so when you have like an example of this, I feel like people don't cook enough to know this, but maybe. I make caramels every Christmas. This is like the one experience I have with this. But you heat up, all this stuff, cream and butter and whatever, and sugar, and you heat it up so that the sugar dissolves. And if you're not careful and you leave like some granules of sugar on the edges of the pan, when it starts to cool down, those granules act as like kind of like a reminder to the sugar that's dissolved that it used to be a solid, and they start to come out of the solution. They form a solid again. And so then you'll get like a really grainy flavor and it's not smooth. I feel like I've noticed this with like homemade fudge sauce before a lot of the time. So that's because it was super saturated as you cooled it down, and it has to have, it's called a nucleation point. That's what this picture is showing. They're adding like a single crystal to a super saturated solution, and the salt that's in there is like, oh yeah, I'm not actually supposed to be dissolved. Like, I remember that I used to be a crystal, I used to be a solid ionic compound, and so then it starts to go back to being a crystal, back to being a solid. Okay, so now we're going to use specific data and just kind of basically use these questions down here to understand how to read a graph like this. So just a quick reminder of how you do it. So like we've got this potassium chlorate here, and we're at, say, 20 degrees Celsius, then it's telling us, so each of these lines is 2 grams, and this is grams of the solute in 100 grams of water. So I'm actually gonna change this question down here. I remember seeing this last year and forgetting to change it in the thing, but we're gonna change that to 100 grams of water. It's just an unnecessary calculation for us to like adjust it to being 100 grams, and it's annoying. So we're gonna call it 100 grams of water. So if you have 100 grams of water at 20 degrees Celsius, you're able to dissolve, it looks like maybe 2.5 grams of potassium chlorate. Okay, so 2.5 grams would dissolve at that temperature. If you added 5 grams in there, 2.5 of it will dissolve and 2.5 of it will be sitting on the bottom of the container. That would be a saturated solution. Some of it's dissolved, some of it's not. Okay, so what I want you to do is do the first, let's say these first 2 questions here. For potassium nitrate, I'm gonna highlight those, potassium nitrate and potassium sulfate. Okay, so those 2 salts, these 2 amounts down here, 25.5 and 4.5, and I want you to tell me if they're not dissolved at all or partially dissolved or fully dissolved at 60 degrees Celsius. Okay, so I'll give you a minute or 2 to do that, and then if you finish, you can go on to the what if we cool them down part. Okay, let's at least look at the first two questions to start. So 60 degrees, and we'll start with this one, 25.5 grams of potassium nitrate. So, oh my goodness, there is like so much potassium nitrate, it's off the chart, okay? So yes, I'm definitely gonna be able to dissolve that 25.5 grams. The other way you can look at it is go to where 25 is and make sure it's under that curve. So 25 is about here. I can dissolve 25 grams starting at close to 15 degrees Celsius. So if I just continue to heat it up, it's gonna stay in there, okay? So yes, it would be fully dissolved at 60 degrees. 4.5 grams of potassium sulfate, okay? So at 60 degrees, I can dissolve, what is that, 18 grams? So 4.5 is fine. I still have room for plenty more, but that would be fully dissolved as well. Okay, so then the next question is, what about if we cool it down to 0 degrees Celsius? So go ahead and come over to 0 and do the same thing and decide, is it fully dissolved or not? And if it's not, how much of it is not dissolved? Like how many grams are going to be sitting on the bottom of that container? Okay, so potassium nitrate, which was the 25.5 grams. So that's this curve up here. So if we come down at 0 degrees Celsius, it looks like only 15 grams can dissolve at 0 degrees Celsius. And I had 25.5 in there. So unless it cooled down really well and was able to be super saturated, which we're assuming it's not, there's going to be 10.5 grams that actually comes out as a solid. Okay, because we're up here, 25.5, you know, there's that 10.5 grams that can't dissolve at that temperature. 10.5 grams will crystallize out. So the solution, another way of thinking of that or talking about it, is that solution is now saturated with that additional mass, you know, crystallized out. And then the potassium sulfate, which was 4.5. Okay, so at 0 degrees Celsius, we can still dissolve all of that. So it's still not saturated at that temperature and that mass. So it's still completely dissolved. There won't be any solid at that point, or it's unsaturated. And then this last question just asks, like, which one will increase in the temperature, which will have the greatest effect on its solubility. So I'm not going to look at those specifically because I don't know why it doesn't answer all of those. But like you can see that the slope tells you which one has the greatest, which change in temperature would most, why can't I get that wording out? Will most greatly, that doesn't make sense at all, will have the greatest impact on the solubility. So potassium nitrate is the one that change in the temperature has the biggest impact. I don't think that was on the list, so like the next one would be ammonium chloride. So you would just look at the slope of the line. Sodium chloride, there's not a big difference there. So changing the temperature does slightly increase the solubility, but not nearly as much as the others. Okay? So the next thing we're going to talk about is gases, because this is specifically how solids are behaving. Gases is the opposite. Gases actually are less soluble at higher temperatures. And this is also something you probably have practical experience with. Obviously, I have a little bit of a Diet Coke habit. But like if you have a Diet Coke out of the pantry and a Diet Coke out of a really cold fridge, and you open them, first of all, it's going to be like a louder hiss coming out of the warm one. That's because there was more CO2 that was not in the liquid phase. So there's always a little bit of room in the top of a closed container where a gas is dissolved to keep that gas in solution. It's called the headspace. So a warm soda versus a cold one, there's more CO2 up in the headspace and less of it in the liquid. And so when you open it, more of that CO2 escapes. And taste-wise, it's going to have less bubbles in it. This is always for a closed system. So gases are only going to dissolve into a liquid if they're contained, because if they're allowed to escape, then the gas will keep dissolving out of the liquid and then spreading out into the air, and they're never going to actually dissolve. So when we dissolve a gas into a liquid, you have to cap it off somehow and create a pressure in that headspace. Once you create that pressure, a certain amount of it will dissolve into the liquid, okay? So there's an equation that accounts for how much pressure of that gas you have to apply to get a certain amount of it to dissolve, okay? So the amount of it that dissolves is called the solubility rule. So it says here the solubility of the gas. Usually this is measured in molarity. So if you remember, we did molarity in chapter 5, moles of the solute. I'll just write it down. Moles of the solute over liters of the solution. So when we say solubility, we mean how soluble is it or how much can dissolve. There's different ways of measuring that how much, okay? The general term is concentration, but do we measure that concentration in molarity? Do we measure it in, like, a lot of cleaning products, household items are measured in a volume percent? There's a lot of different ways to measure concentration. For this particular equation, it's calculated in molarity because that's what the constant for each gas is given in. So every gas is going to have a unique ability to dissolve into a liquid, and all of these are going to be at 25 degrees Celsius, okay? So the units there are molarity per atmosphere. So let's look at CO2 specifically. I know I highlighted oxygen, but there we go. So for every atmosphere of gas, of CO2 gas that you apply over the top of a liquid, you're going to be able to get 0.034 moles to dissolve in every liter. So like a liter is, like think of a 2-liter bottle, okay? So you would be able to get 0.034 times 2 moles of CO2 to dissolve in that 2-liter bottle for every atmosphere of CO2 that you put above the liquid. you can feel, you know, a bottle of soda. There's a higher pressure, obviously, inside the bottle. That's why it hisses when you open it. That's why it feels firm. So it must be more than 1 atmosphere that's in that bottle. So we're going to calculate in using this equation with the next one. Let's say that we want it to be 0.12 molar. We want to know what pressure of CO2 do we have to inject into that bottle in order to get it to be that concentration or that molarity of CO2, okay? So don't forget, solubility, concentration, in this case molarity, those are all equivalent. So go ahead and use that equation and calculate what pressure is necessary to keep that molarity. All right, so 3.5 atmospheres. So it's quite a bit. I don't know if 0.12 molar, that must be a normal concentration of carbon dioxide in soda. But 3.5 atmospheres, that's pretty significant. 3.5 times normal atmospheric pressure that you have to inject. You know, they have to like put this into the bottle and not allow it to escape as they're doing this. They probably do it at really cold temperatures because, like we said, the colder a liquid is, the more gas you can get to dissolve. So they probably do it at a very cold temperature before they seal it off. So pretty high pressure to get that concentration. You'll always be given the constant because it's dependent on a particular gas. Obviously, it's not something you have to memorize. Okay? So we'll just do one more concept-based question. So it says that it's saturated. This solution is saturated in nitrogen gas and potassium bromide, which is going to be a solid. an ionic compound, at a high temperature, 75 degrees C. And then you cool it down to room temperature, what's most likely to happen? Okay, so you've got all the gas you can dissolve, all the potassium bromide that you can dissolve, and then you cool it down. Okay, so take a minute and read through those options and see which one makes the most sense with what we know about how solubility is affected by temperature. Okay, so cooling it down, it says some nitrogen gas bubbles out of solution. No, gases actually become more soluble the cooler it is, so that can't be correct. If anything, we would see more of the nitrogen go into the solution. It would actually become more concentrated in nitrogen gas. Some potassium bromide precipitates out of the solution. Precipitates means it goes from the solution to a solid. It's like the opposite of dissolving. So yeah, definitely some of that would happen. So I'm going to go yes on this one. The last one, some nitrogen bubbles out. No, we already said that doesn't happen, so it can't be that. And nothing happens, no. So it's B. You'll get some of that solid dropping out of solution or precipitating out of solution. So it will have all been dissolved, and then some of it will come out as a solid. Okay? So just as a quick preview, on Friday, we're going to do a lot of math. So make sure you have your calculator, get your math brain with you that day. You could do a little bit of this ahead of time if you want to make sure you're not confused. But we're going to do all those other concentration units other than just molarity. So there's a lot of different ways to measure it, like I mentioned, and we need to be familiar with quite a few of them in order to use them in different calculations moving forward. Okay? All right, I will see you guys then.
Can you go into the last slide real quick?
Yep. How did I know? I was like, I'll go back.
So basically, was B the only one that was likely to happen?
Yeah.
Yeah.
So it's possible that some nitrogen might dissolve too, but that wasn't an option. So